In this video, we're trying to make a very simple measurement. We're asking ourselves a question: what is the mass of a resistor? So this is a 1/2 watt resistor, and I'd like to know the mass of it. I have a kitchen balance, which has precision up to 2 decimal places, and obviously I can just go ahead and put that resistor on the balance there, and it measures 0.33 grams. Now, if I want to get a little more precision, remember precision is a measure of the reproducibility, we can take the resistor off. I'm going to tear the balance to make sure that it is reading 0 and try it again. And this time I get something a little bit different. So I could do this several times. And when I do that, I get a series of values that I can calculate an average and a standard deviation for. In Excel, if I'm going to do an average, then for any function in Excel, I need to start with an equal sign to let it know that I'm going to use a function. Type in the average and then as the name of the function, and then the arguments for that function, I can just drag out the 5 values that I want. And that gives me the average, 0.354. Standard deviation, we do the same thing. STDev is the abbreviation. There are 2 different STDevs. There's a population and a sample. Since I only took a sample, one sample of all of the resistors ever made, then you're going to be using the sample standard deviation. So they do that. Oops. stdev.s. And again, we map out the 5 values that we're interested in, not the average. It's the standard deviation is based on the values that we measured, and we get that. Now, if I go to the standard deviation, we always only report standard deviations to 1 decimal place, to 1 significant figure. So I moved my decimal places to get to that. And then I need to adjust my average so that it only goes out as far as that decimal place. So if the standard deviation only goes out to the 100th place, then my average can only go out to the 100th place. The units of both of these are grams. And we now have a value. So for this the mass of this particular resistor, 0.35 plus or minus 0.02 grams for this particular resistor. Let's calculate one more value. We're going to call this the RSD, standing for the relative standard deviation. The relative standard deviation can be calculated from the ratio of the standard deviation, so standard deviation divided by the average times 100. So let me sit on that for just a second so you see how we're plugging into an equation into Excel. Notice there aren't any functions for calculating RSD in Excel, so we're making an equation manually, just like we would plug into a calculator. And we start off again with the equal sign to indicate that we're doing an equation, and then where the values actually show up, the 0.36 and the 0.02 are the B7 and the B8. Multiplication is the asterisk, shift 8 times 100, and there we are. And we are going to be a little bit flippant with our sig figs and standard deviations, and we are typically going to report relative standard deviations to 2 sig figs. And this isn't quite legit, but we're not going to use RSDs for any sort of significance testing. So that's the way we'll work it. Now there's a problem with the method that we just used. We saw that we found the mass of one resistor, and we have some level of precision, 5%, roughly 5% relative error. The that turns out to not be a very good number. That's a little bit high, and we want to try to improve that a little bit. Also, we've only got the mass of this one resistor, and I've got this whole pile of resistors. So let's see if we can do a little better job by measuring the mass of a bunch of different resistors. So let's go ahead and measure 10 resistors. Okay, I've got the data there. We're going to pause the video. I'd like you to try to use those equations. If you're following along, see if you can calculate the average standard deviation and relative standard deviation of this set of 10 data points. Okay, you should have used the average function, drawn out those 10, and gotten a value somewhere around there. Remember to use the standard deviation equation for a sample. And then before we go forward, let's go ahead and adjust these numbers to give us just one significant digit there. That means I need to remove this here. And then the relative standard deviation is the ratio of these two numbers times 100. Okay. Now, it looks like we have improved our precision just a little bit. Went from 4.6 to 3.6. Notice how the absolute standard deviation, plus or minus 0.01, has decreased by just a wee little bit. And that's what caused our RSD to improve. Notice how I'm not putting any units in for RSD. If RSD is calculated from the ratio of grams and grams, then the grams would cancel out, and that's why this number here is unitless. So we get a little bit of an improvement here, but that may just be luck. I would be surprised if this is a huge improvement. So we need to come up with a better way to try to improve our precision of this measurement. So instead of measuring one resistor at a time, why don't we measure a bunch of resistors? And then what we'll do is, I've got 15 resistors in my hand here. You'll have to trust me on that. We'll see whether, how you can not trust me and prove it for yourself later on in the video. But I'll take 15 resistors and I just plop them down right there. And if we know that these resistors weighs 5.58 grams, then that means the average mass of a resistor can be calculated by taking that number and dividing by 15. And we do get a number that's reasonably close. Notice how we don't get any information that allows us to calculate a standard deviation here. So we don't have any assessment at this point as to the precision of this value. So let's go ahead and do this measurement multiple times. Okay, instead of copying and typing in this equation the same way, since it's the same equation as we go down this column, all that changes is that instead of using B27, it's going to use B28, B29, so on and so forth. What I can do is just click this little box right here in the lower right-hand corner. Notice how my cursor changes. If I click and then drag the mouse down, it changes the units, or it changes the equation and it calculates as appropriate. So I'm going to adjust these. And right now I don't know what the correct number of digits is that I should use, so I'm just going to put in 3. And now let's do the average and the standard deviation. and we'll calculate the RSD. Change this to 2 decimal places, or 2 sig figs, and notice how our precision has increased dramatically. We've gone from 3.6% down to 0.3%. So we've, by adjusting and measuring the mass of a number of multiple resistors, I was able to improve the precision of the result dramatically. And part of the reason for that, if you noticed, when we're just measuring one resistor, we're only using 2 decimal place, or 2 of the digits, the places on our balance. And as we move up to the whole full 15, we now have 3 sig figs in this number that's being reported by the balance, and that's reflected in our statistics, in our summary statistics or descriptive statistics that we've been using so far. Now, we can ask ourselves a question, how many is enough? I chose 15. Let's do the same exact thing with 5 resistors and see if we get the same result. Okay, and what we see here is that the improvement is still much better than when we did the individual resistor. However, the performance is slightly worse than when we use 15 resistors. So in general, using a larger quantity of material to perform a measurement is going to lead to higher relative precision. Sometimes the absolute precision is going to be a little bit different. It doesn't show off in this particular data set, but this number here, the percent RSD, is going to change. It's going to be dependent on the size of the sample that we use, with the smaller RSD coming from the larger sample size. One last comment that I want to make about these data that we've collected today is summarized in this table. We've got the 4 cases where case 1 was just the single resistor multiple times. Case 2 were the 10 resistors measured each once. Case 3 was the set of 15 resistors measured several times. And case 4 was the 5 resistors measured multiple times. We see that the average resistor mass obtained from each one is all pretty close together. However, in cases 1 and 2, we were limited to about 2 significant figures, and we see that the relative standard deviation was around 5%. It was greater than 1% here, and that indicated only about 2 sig figs. When we went to the aggregate cases, we saw that we were able to extend out to 3 decimal places, 3 sig figs. Again, similar values, smaller RSDs, percent RSDs, with the best case being the largest of the 2 aggregates. If we take a look at the standard deviations of the measured values, not the values after we process them, but just the measured values, we see that they fall around 0.01 to 0.02. And if you recall from taking a look at the instrument, at the digital balance, that's the final decimal place that is displayed on the balance. And so we can get an estimate of the instrument uncertainty by performing these measurements multiple times, but by performing the same measurement multiple times. So that's one of our takeaways. Our first takeaway is that percent RSD is a measure of the precision. Second comment that I want to make is that generally we're going to be aiming for RSDs that are percentages that are less than 1%. I just mentioned this. When we talk about instrument uncertainty, very often that's a number that we just get from a text or provided by a supplier, the provider of the instrumentation, but we could confirm that number by making the same measurement repeatedly. And in summary, we saw that aggregate measurements lead to better precision, with the larger sample sizes leading to the better or the best precision that we saw today.